Okay, welcome back everyone. In this example, we're going to be looking at using conservation of energy for a system that involves rotation. And so what we've got basically is a fixed cylinder and a fixed disc attached to a ceiling, and a thread is going wrapped around the cylinder, and it goes over the disc or pulley and attaches to a box of mass 3 kilograms. And so we're given the radius and mass of the cylinder and the disc, and we're also given the fact that the box falls a distance of negative 2.50 meters, and we're asked to use energy in order to determine the final speed, VB, of the box. Okay, so we could use forces, and we could set up a system of equations whereby we calculate T1 between the cylinder and the disc, and T2 between the disc and the box, and we write 3 equations with lots of unknowns. But it turns out that it's easier to use conservation of energy. And so once again, we will say that the total change in energy is equal to 0. So the change in kinetic plus the change in potential is equal to 0. And now we just start setting these up. Now there's going to be 3 kinetic energy terms, and each of the initials are equal to 0. Okay, so we can say that this is where height initial is equal to 0 and K initial is equal to 0 for the system, because it starts at rest. Okay, so basically what we can say is that the final kinetic energy of the cylinder plus the final kinetic energy of the disc plus the final kinetic energy of the box is going to be equal to the negative potential energy final of the box. And so we know that when an object is rotating, instead of having a translational kinetic energy of 1/2 mv squared, we must use the rotational kinetic energy, 1/2 I omega squared. And so for the cylinder, we'll have 1/2 I of the cylinder times omega of the cylinder squared plus 1/2 I of the disc times omega squared of the disc plus 1/2 mass of the box, speed of the box squared. And that's going to be equal to negative mg delta y of the box. Okay. Now, at this point, we can do a couple things. First of all, we can plug in an equation for the moment of inertia. Okay, so the cylinder and the disc both have the same moment of inertia, basically 1/2 m r squared. That's the same thing for the cylinder and the disc. So we get 1/2 mass of cylinder, radius of cylinder squared, and we can also make use of the fact, I'm going to go over here, that omega is v divided by r. So this is going to be that omega squared of the cylinder is going to be v of the string, which is the point at the edge of the radius, right? But that's basically the speed of the box squared over the radius of the cylinder squared. So we get some great cancellation there. Then we do the same thing with the disc, 1/2 mass of disc, radius of disc squared, and we have VB squared over radius of disc squared. Once again, nice cancellation. And we have 1/2 mass of box, V box squared, equals M box G delta Y, and there is a negative sign. So I'll plug in some numbers. Okay, this is going to be 1/4 times 5 times v box squared plus 1/4 times 2 times v box squared plus a simple 1/2 times 3 mass of the box times v box squared. That's going to be negative 3, 9.8, negative 2.5. So those will cancel. Alright, and so at this point you can collect terms and solve for the speed of the box, and if you do everything correctly, it comes out to be approximately 4.76 meters per second. And so the idea with this problem is that using energy methods makes it a lot easier.